The IEEE Standard for Floating-Point Arithmetic is a technical standard for floating-point computation established in 1985 by the Institute of Electrical and Electronics Engineers. Many hardware floating-point units use the IEEE 754 standard. The standard addressed many problems found in the diverse floating-point implementations that made them difficult to use reliably and portably. The current version, IEEE 754-2008, published in August 2008, includes nearly all of the original IEEE 754-1985 standard and the IEEE standard for radix-independent floating-point arithmetic. The international standard ISO, IEC, IEEE 60559-2011 has been approved for adoption through JTC 1, SC 25 under the ISO, IEEE PSDO agreement and published. The standard defines arithmetic formats, sets of binary and decimal floating-point data, which consist of finite numbers, infinities, and special, not a number, values, interchange formats, encodings that may be used to exchange floating-point data in an efficient and compact form, rounding rules, properties to be satisfied when rounding numbers during arithmetic and conversions, operations, arithmetic, and other operations on arithmetic formats, exception handling, indications of exceptional conditions. The standard also includes extensive recommendations for advanced exception handling, additional operations, expression evaluation, and for achieving reproducible results. The standard is derived from and replaces IEEE 754-1985, the previous version, following a 7-year revision process, chaired by Dan Zuras and edited by Mike Cowlishaw. The binary formats in the original standard are included in the new standard along with 3 new basic formats. To conform to the current standard, an implementation must implement at least one of the basic formats as both an arithmetic format and an interchange format. As of September 2015, the standard is being revised to incorporate clarifications and errata formats. An IEEE 754 format is a set of representations of numerical values and symbols. A format may also include how the set is encoded. A format comprises finite numbers, which may be either base 2 or base 10. Each finite number is described by 3 integers. S equals a sign, C equals a significand, Q equals an exponent. The numerical value of a finite number is S times C times BQ, where B is the base, also called radix. For example, if the base is 10, the sign is 1, the significand is 12,345, and the exponent is -3. Then the value of the number is -11 times 12,345 times 10 minus 3 equals -1 times 12,345 times 001 equals -12.345. 2 infinities. Plus infinity and minus infinity. 2 kinds of NaN. A quiet NaN and a signaling NaN. A NaN may carry a payload that is intended for diagnostic information indicating the source of the NaN. The sign of a NaN has no meaning, but it may be predictable in some circumstances. The possible finite values that can be represented in a format are determined by the base b, the number of digits in the significand, and the exponent parameter in max. C must be an integer in the range 0 through bp-1. Q must be an integer such that 1 minus a max Q plus p minus 1 a max. Hence the smallest non-zero positive number that can be represented is 1 times 10 minus 101, and the largest is 9,999,999 times 1090. And the full range of numbers is -9.9999999 times 1096 through 9.9999999 times 1096. The numbers minus b1 minus a max and b1 minus a max are the smallest normal numbers. Non-zero numbers between these smallest numbers are called subnormal numbers. Zero values are finite values with significand zero. These are signed zeros. The sign bit specifies if a zero is plus 0 or minus 0. Representation and encoding in memory. Some numbers may have several representations in the model that has just been described. For instance, if b equals 10 and p equals 7, minus 12.345 can be represented by minus 12,345 times 10 minus 3, minus 123,450 times 10 minus 4, and minus 1,234,500 times 10 minus 5. However, for most operations, such as arithmetic operations, the result does not depend on the representation of the inputs. For the decimal formats, any representation is valid, and the set of these representations is called a cohort. When a result can have several representations, the standard specifies which member of the cohort is chosen. On the contrary, for the binary formats, the representation is made unique by choosing the smallest representable exponent. In particular, in the normal range, the leading bit of the significand is non-zero, thus always 1. As a consequence, this leading bit, one of the normal numbers, need not be represented in the memory encoding. This rule is called leading bit convention, implicit bit convention, or hidden bit convention. Basic and interchange formats. The standard defines 5 basic formats that are named for their numeric base and the number of bits used in their interchange encoding. There are 3 binary floating point basic formats and 2 decimal floating point basic formats. The binary 32 and binary 64 formats are the single and double formats of IEEE 754-1985. A conforming implementation must fully implement at least one of the basic formats. The standard also defines interchange formats, which generalize these basic formats. For the binary ones, the leading bit convention is required. The following table summarizes the smallest interchange formats. Note that in the table above, the minimum exponents listed are for normal numbers. The special subnormal number representation allows even smaller numbers to be represented. For example, the smallest double precision number greater than 0 that can be represented in that form is 2 minus 1074. Decimal digits is digits times log 10 base. This gives an approximate precision in decimal. Decimal Emax is a max times log 10 base. This gives the maximum exponent in decimal. As stated previously, the binary 32 and binary 64 formats are identical to the single and double formats respectively of IEEE 754-1985 and are 2 of the most common formats used today. The figure below shows the absolute precision for both the binary 32 and binary 64 formats in the range of 10-12 to 10+12. Such a figure can be used to select an appropriate format given the expected value of a number and the required precision. Extended and extendable precision formats. The standard specifies extended and extendable precision formats, which are recommended for allowing a greater precision than that provided by the basic formats. An extended precision format extends a basic format by using more precision and more exponent range. An extendable precision format allows the user to specify the precision and exponent range. An implementation may use whatever internal representation it chooses for such formats. All that needs to be defined are its parameters. These parameters uniquely describe the set of finite numbers that it can represent. The standard does not require an implementation to support extended or extendable precision formats. The standard recommends that languages provide a method of specifying p and a max for each supported base b. The standard recommends that languages and implementations support an extended format which has a greater precision than the largest basic format supported for each radix b. For an extended format with a precision between two basic formats, the exponent range must be as great as that of the next wider basic format. So for instance, a 64-bit extended precision binary number must have a max of at least 16,383. The x87 80-bit extended format meets this requirement. Interchange formats are intended for the exchange of floating-point data using a fixed-length bit string for a given format. For the exchange of binary floating-point numbers, interchange formats of length 16 bits, 32 bits, 64 bits, and any multiple of 32 bits 128 are defined. The 16-bit format is intended for the exchange or storage of small numbers. The encoding scheme for these binary interchange formats is the same as that of IEEE 754-1985. A sign bit, followed by W exponent bits that describe the exponent offset by a bias, and P-1 bits that describe the significand. The width of the exponent field for a k-bit format is computed as W equals round minus 13. The existing 64 and 128-bit formats follow this rule, but the 16 and 32-bit formats have more exponent bits than this formula would provide. As with IEEE 754-1985, there is some flexibility in the encoding of signaling NaN. For the exchange of decimal floating-point numbers, interchange formats of any multiple of 32 bits are defined. The encoding scheme for the decimal interchange format similarly encodes the sign, exponent, and significand, but two different bit-level representations are defined. Interchange is complicated by the fact that some external indicator of the representation in use is required. The two options allow the significand to be encoded as a compressed sequence of decimal digits or alternatively as a binary integer. The former is more convenient for direct hardware implementation of the standard, while the latter is more suited to software emulation on a binary computer. In either case, the set of numbers that may be encoded is identical, and special values have identical binary representations. Rounding rules. The standard defines 5 rounding rules. The first two round to a nearest value, the others are called directed roundings. Roundings to nearest round to nearest. Ties to even, rounds to the nearest value. If the number falls midway, it is rounded to the nearest value with an even least significant bit, which occurs 50% of the time. This is the default for binary floating point and the recommended default for decimal. Round to nearest. Ties away from 0, rounds to the nearest value. If the number falls midway, it is rounded to the nearest value above or below. This is intended as an option for decimal floating point. Directed roundings round towards 0, directed rounding towards 0. Round toward plus infinity, directed rounding towards positive infinity. Round toward minus infinity, directed rounding towards negative infinity. Required operations. Required operations for a supported arithmetic format include arithmetic operations, conversions, scaling and quantizing, copying and manipulating the sign, comparisons and total ordering, classification and testing for nans, etc., testing and setting flags, miscellaneous operations, total ordering predicate. The standard provides a predicate total order which defines a total ordering for all floating numbers for each format. The predicate agrees with the normal comparison operations when they say one floating point number is less than another. The normal comparison operations, however, treat nans as unordered and compare -0 and +0 as equal. The total order predicate will order these cases, and it also distinguishes between different representations of nans and between the same decimal floating point number encoded in different ways. Exception handling. The standard defines 5 exceptions, each of which returns her default value and has a corresponding status flag that is raised when the exception occurs. No other exception handling is required, but additional non-default alternatives are recommended. The 5 possible exceptions are: invalid operation, division by zero, overflow, underflow, and is inexact. Inexact. These are the same 5 exceptions as were defined in IEEE 754-1985, but the division by zero exception has been extended to operations other than the division. For decimal floating point, there are additional exceptions along with the above. Clamped. By default, trailing zeros will be added to the coefficient to reduce the exponent to the largest usable value. If this is not possible, then overflow occurs. Rounded. The inexact is signaled if any non-zero digits are discarded. Additionally, operations like quantize when either operand is infinite, or when the result does not fit the destination format, will also signal invalid operation exception. Recommendations. Alternate exception handling. The standard recommends optional exception handling in various forms, including pre-substitution of user-defined default values, and traps and other exception handling models which interrupt the flow, such as try, catch. The traps and other exception mechanisms remain optional, as they were in IEEE 754-1985. Recommended operations. Clause 9 in the standard recommends 50 operations that language standards should define. These are all optional. Recommended arithmetic operations, which must round correctly. X, 2x, 10x, x minus 1, 2x minus 1, 10x minus 1 log 2, log 10 log 2, log 10 square root x2 plus y2 1, square root xn x1, nxn, xy sin, cos, tan asin, ACOs, atin, atin 2 sin pi equals sin, cos p equals cos atin pi equals atin, pi, atin 2 pi equals atin 2, pi shine, cosh, tan h asin, a cosh, r tan the asinpi, acospi and tan pi functions are not part of the standard because the feeling was that they were less necessary. The first 2 are mentioned in a paragraph, but this is regarded as an error. The operations also include setting and accessing dynamic mode, rounding direction, and implementation. Defined vector reduction operations such as sum, scaled product, and dot product, whose accuracy is unspecified by the standard. Expression evaluation. The standard recommends how language standards should specify the semantics of sequences of operations, and points out the subtleties of literal meanings and optimizations that change the value of a result. By contrast, the previous 1985 version of the standard left aspects of the language interface unspecified, which led to inconsistent behavior between compilers, or different optimization levels in a single compiler. Programming languages should allow a user to specify a minimum precision for intermediate calculations of expressions for each radix. This is referred to as preferred width in the standard, and it should be possible to set this on a per-block basis. Intermediate calculations within expressions should be calculated, and any temporaries saved, using the maximum of the width of the operands and the preferred width, if set. Thus, for instance, a compiler targeting x87 floating-point hardware should have a means of specifying that intermediate calculations must use doubled, extended format. The stored value of a variable must always be used when evaluating subsequent expressions, rather than any precursor from before rounding and assigning to the variable. Reproducibility. The IEEE 754-1985 allowed many variations in implementations. IEEE 754-2008 has tightened up many of these, but a few variations still remain. The reproducibility clause recommends that language standards should provide a means to write reproducible programs, and describes what needs to be done to achieve reproducible results. Character representation. The standard requires operations to convert between basic formats and external character sequence formats. Conversions to and from a decimal character format are required for all formats. Conversion to an external character sequence must be such that conversion back using round to even will recover the original number. There is no requirement to preserve the payload of a NaN or signaling NaN, and conversion from the external character sequence may turn a signaling NaN into a quiet NaN. The original binary value will be preserved by converting to decimal and back again using 5 decimal digits for binary 16, 9 decimal digits for binary 32, 17 decimal digits for binary 64, 36 decimal digits for binary 128. For other binary formats, the required number of decimal digits is where P is the number of significant bits in the binary format, e.g., 24 bits for binary 32. When using a decimal floating point format, the decimal representation will be preserved using 7 decimal digits for decimal 32, 16 decimal digits for decimal 64, 34 decimal digits for decimal 128. Algorithms with code for correctly rounded conversion from binary to decimal and decimal to binary are discussed in and for testing in